This case study, demonstrating how Starbucks used response surface designs to fine-tune their coffee packaging process, is brought to you by JMC Data Experts. Customer surveys identified the packaging of Starbucks £1 mass coffee bags as an important customer satisfaction issue. The airtight seal of the bag prevents the coffee from oxidizing. However, the easy open and reseal features are also important. If the inner lining of the bag tears or the seal is too tight, the customer can have coffee spilling all over the floor. Starbucks needed to find a way to seal the bags really well, but not too well, essentially threading the needle for these two responses. Response surface methodology is a collection of experiment designs and statistical analysis tools used to develop second-order models for multiple responses, allowing the experimenter to optimize them simultaneously. Since these experiments are much larger than factorial designs, response surface designs are used mainly to hit very tight process requirements. Several factorial designs were used to reduce the long list of potential variables to 3 key variables: jaw compression pressure, melting viscosity of the plastic, and the gap between the 2 sealing plates. A central composite design was used to collect all the data needed to develop response surface maps for each of our responses: leak and tear. The central composite design has some distinct advantages. For example, the 2 to the 3rd factorial portion of the experiment can be run first, and then the axial data points shown in red can be added if curvature is found. This is called sequential experimentation. Secondly, the property of rotatability ensures the prediction variability at any point the same distance from the center of the design will be equal. Finally, notice that 5 levels of each variable are tested. This helps prevent hopping over a sweet spot in the response, which is especially problematic if the response is binary. Box-Behncke is another common response surface design. Its main advantage is fewer runs compared to the central composite. If there are 3 or 4 variables and run economy is important, Box-Behncke is a good choice. Secondly, as shown in the design space diagram, Box-Behncke avoids any extreme values in the design space. The corners and the axial points are not run as they are in the central composite. Finally, this design can be easier to carry out because there are only 3 levels of each variable to study. The success of Sarah Burrows' experiment was documented in a Quality Progress article in March of 2011. Beyond the sound principles of the central composite, 3 other features were key to her success. First, information from previous factorial experiments was used to estimate the sweet spot for the center of the design. For the central composite to be successful, it should be centered near promising process settings. Secondly, her responses were binary when measured in standard production, but they were then converted to continuous measurements for the experiment. This added power to the design. Finally, the center points were spread equally through the experiment so that they could be used as a control for the stability of the process. This turned out to be key to the analysis of the results. Analysis of the experiment results led to an equation for each response as a function of the process variables. Noting that the responses showed the least sensitivity to plastic viscosity, viscosity was held constant at its low setting, and the resulting equations were then visualized simultaneously with the overlaid contour plot. The plot shows that the variable space where both defects are minimized is pressure between 184 and 190 psi, and plate gap between 1 and 2.4 millimeters. These settings were tested in a verification run of 60 samples, and then successfully implemented on one line, confirming the experimental results. Implementation of the improved process across all lines eliminated leak defects, while reducing tear to 1/10 of its benchmark level. Customer complaints were reduced accordingly. Sarah succeeded in threading the needle between these 2 competing responses. She went on to become a 6 Sigma Master Black Belt with Alpha 6 Sigma in Palm Desert, California. If you would like to use response surface designs to optimize a particularly sensitive process, or if you have questions about this case study, contact us at JMC Data Experts.